now that the unpleasantness is over, let's. All right, so we're working on capacitors in parallel. Okay, so what we started by saying the capacitance of a single equivalent capacitor. That is going to be now I will say you're going to want to make sure you get how to do this stuff because your assignment at the end of this week is going to be filled with a lot of this fun stuff.
That's not a hard assignment.
No, because for circuits, there's not really any derivations to do. Like the equations are kind of what they are. Like you just start your problem by saying, this is what I'm using, then plug in your numbers. So let's see, the charge on the 12 microfarad capacitor. Let's see. Now, we know that the equation for charge what numbers am I going to plug into this? So like if you're doing your homework, you start here, then you plug in numbers and go. Yeah, so why? Because it's what? Yeah, in particular, why do you know that it's the same voltage for each one? It's in parallel. So yeah, they all have the same voltage. So that's going to be, so what we have the 12. If they're in parallel, they always have the same delta V. If they're in series, huh? No, you don't have to. But if they're in series, they have the same current and the same charge. Parallel will have different currents because, of course, you see at the junction, the current's going to split. So your charge is going to be when you're doing your homework, you can just leave it in SI units like coulombs. But I just want to make sure you understand how to go from 10 to the negative fourth coulombs to 216 microcoulombs. All right, so part C, the total charge contained in the circuit. Okay, so if we're doing a total anything of the circuit, what do we use? Yeah. Because for a total anything in the circuit, we can take this and use the equivalent capacitor. So that's those four capacitors combined into one. You could redraw the circuit. So you could redraw it like that. Because that's what you've done. You've combined them all into a single capacitor. So this is going to be in your delta V. No, not zero. Now, part D. I would leave, I'd probably leave this one off your assignment, just, I don't know, depends on how I'm feeling when I write it. So an expression for the fraction of total charge contained in one of the capacitors. So we can start by making a fraction. The charge of capacitor I, total charge. So what this would be the capacitance of capacitor I delta V. Now, what capacitance do I use for total charge? So the fraction would be the capacitance of capacitor I over CEQ. So you see that again, the math on circuits is not that difficult. Circuits are already, if anything, are more conceptual because you have to think about, well, now I've taken all these resistors or capacitors and I've smushed them together into a single one. What does that do? Oh boy. Uh-huh. Now, I would learn how to solve stuff like this because this is what your homework's going to look like. In some ways, yes. I would look up, like, if you really kind of want to see or start to get an idea of what your circuit boards look up RLC circuits. Look up RLC circuit diagrams. Resistance, inductance, capacitance.
Oh.
Nope, RLC. Because I is used for current. Now, look up diagrams with logic circuits. Yeah, logic circuit diagrams. Okay, so calculate the equivalent capacitance of the system. So let's see, the battery goes up to a system in parallel. That system in parallel has a top and a bottom that's in series, but then those series have their own parallels. So it's like, so let's start by combining these parallel capacitors, okay? So I'm just going to call the top one CEQ1. Oh, so let's do, so that's going to be C1.0. Okay, so then your CEQ2 will be the bottom one. That's going to be C6.0. Well, there you have 8.0 microfarads. Now we can kind of redraw this. So that that circuit in the so that entire element in the top sometimes it helps to redraw what you've done. Okay, because then instead of the parallels on the top and the bottom, you're going to have 4.0, 4.0, and then 8 and 8. Okay, now I need to combine the series on top and the series on bottom. Okay, so I'll do top first. And so if I have if I have this fraction, what does the CEQ end up equaling? Because I can do most of this without a calculator. I have 1/4 plus 1/4, that's 2/4. 2/4 is 1/2. So if I have, well, that's one, no, I'm asking what the equivalent capacitance is. Yeah, which is what? 2. Nope. Okay. So then let's do the CEQ of the bottom series. All right, so what do we have? Well, we've combined the series on the top and the bottom. Into this. So that's going to be 4.0. Now I need to combine the last parallel. That's the equivalent capacitance of the whole thing. So see, again, the math is not exactly the hardest part. It's how are you going to start breaking this down into smaller and smaller pieces?
Series.
But the 1/4 is for series. Yeah, so we break these down into single capacitors, which are here and here. Okay. Those are in parallel. Then we have series on the top and the bottom. The series is going to be 1/, equivalent capacitance. So we figure out the equivalent capacitance for the top and the bottom, here and here, and then we add those together because they're in parallel again. Yeah. Okay. So what does part B say? Find the charge on the 3 microfarad capacitor from the first diagram. So picked a single capacitor out of that mess and said, what's the charge there? Okay, so you know how we used Kirchhoff's rules to analyze circuits? This is the other way to do it. Combining and then spacing back out. So we say, well, if I go back to this one right here, and I know well, kind of. We're working on breaking this apart. Because we know that as we condense this down, this whole thing here is connected to our battery. Okay, and our battery is what? 12 volts? 12 volts. So I know that both of those have the same delta V. Okay. And I also know that the capacitor I'm shooting for is on the top. So I don't even care about the 4 microfarad capacitor on the bottom. I'm just looking at the capacitor on the top, and I'm going to start spacing that back out. So let's find the charge there. Okay, so. This is going to give me 2.4 times 10 to the negative fifth coulombs, or 24 microcoulombs. Okay, now I'm going to go back to this one. I have the charge for the top. So those two, so the two in parallel have the same delta V. Let's also remember that as we space this back out. So what can I say about the, so again, I'm only worried about the top. Okay, because that's where that three microfarad capacitor is going to be. What can I say about these two? Same charge. So what I want to do is, okay, so this, let me see if you can. So that 4 microfarad capacitor, I'm going to have to end up spacing it back out. What do I want to calculate that I can then take into the next calculation? Because this one will space into what? Yeah, 2 capacitors that are in parallel. What can I use that will allow me to calculate both of those? Voltage, delta V. I want the delta V of that 4.0, so when I space it apart and they become parallel again, they both have the same delta V. So that's kind of the way I space it back out. I go from same delta V to same Q to same delta V to same Q, so on and so forth. Yeah. Yep. And on your homework, I will actually put down, use Kirchhoff's rules for this one. Use, I don't know, I'll call this the combination method. But because I don't want you to just go, Kirchhoff's easier, I'm going to use that for all of them. No, you got to practice both. So what we want is, so we want the delta V, that's going to be Q. Okay. And that Q is one is what we just calculated. And then, so for that is going to give me 6 volts. All right. And then I'm just going to take this original parallel system and say, well, now I have because again, if I'm just looking at the top, then I have this capacitor over here. And I know that the delta V here and so now if I want the Q, that would help your performance in football. You're not going to run up and down a field while smoking. What? Well, that took a dark turn. That took a dark turn. Although although after watching the Olympics, I think that the Canadian hockey team spent time ice fishing in Quebec. That's,
Yeah, they did.
I know.
So this will give us 1.8. You won't turn it. Or 18 microcoulombs. Again, if you just want to leave it in coulombs, that's fine. So these are your two methods. You can use Kirchhoff's rules or you can do these. Now, keep in mind, you could figure this out using Kirchhoff. You could. It would end up being a little more difficult than the ones you did. Kirchhoff is also usually more applicable to combination circuits. So you remember how we had resistors and capacitors in those? So Kirchhoff usually makes those quite a bit easier. That's why you would usually choose to use those there. And here, like for something like this, you would just do the combination method. Because again, Kirchhoff could get pretty intense here because like the first thing you'd have to figure out is current to use Kirchhoff. Could be done though. Uh-oh. Uh-oh. Let's see. Man, time just goes too, you don't have enough time to get through everything. All right, well, okay. So same idea. Find the equivalent resistance of the circuit and what is the current in each resistor. All right. So let's start by combining the resistors that are in parallel. So for resistors in parallel, how do we do that? 1 over. Again, remember your resistors and your capacitors are pretty much the inverses of each other. Yeah, let's see, that's 1 over 6 plus 2 over 6. That's okay, so we have 2.0 for that if we combine that that parallel section. So then what that's going to give us and this is why I try to draw the diagrams before I come to class. Because what? So again, what we have is, so this will still be the 8 ohm. This one will still be the 4 ohm. And now your what was a parallel system, you now have 2 ohms. And now the equivalent resistance so now they all share the same current. And so so it's going to be 14 ohms. Yeah, some are harder, some are easier. Oh yeah. So that well, so you put 1 over, so you put 1 over 0.5 is what you would do. So, I mean, that's valid. You can do that. Because because the way I do it in my head is I say, well, that's going to be 1/2, that equals 2. Yeah, yeah, that's what you're doing. When you invert a fraction, you flip it upside down. Yeah. You can also compare the two sides. So if they both have the same format, the resistance equals 2. Now, part B, what is the current in each resistor? Well, first thing I need to know is total current. Then I need to split it into I1 and I2. Yep. So we'll go there. Current. So the delta V of our battery was what, 42 volts? We'll get there. You want the total current. When they're in series like this, they all share the same current. It doesn't matter. Because then what we need to do is, we need to take this current, go back to the 2.0 ohms and break it back into its parallel. You could. I'm not saying you can't. Yeah, I'm not saying you can't do that. I'm just. No, you don't have to. You can start with your expression for I. Again, when you're doing these on assignments, I'm not like, I want to see the equation you start with that you're going to plug numbers into. I also want to see you drawing diagrams. Mm-hmm. I'm going to get cigarette burns in your assignment, crayons on hers. Honestly, you should draw your circuits in crayon. Boy, that's the truth. Okay, so we know that I is 3 amps. That's as far as I'm going with that conversation. Face got a little red. What happened? Okay. Yeah. So, because, yeah, let's do that. What is the current in each? So, okay. So we already know that for the 8 and the 4 ohm, it's 3 amps. Okay. Now we need the 6 and the 6 ohm and the 3 ohm. Okay. 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 So what we need is the delta V for that 2 ohm equivalent resistance. Okay. So this will give it, so it's 3 amps. 2 ohms. It's going to be 6 volts. Okay, now so now we have this parallel where you have the 6 ohm and the 3 ohm from the original diagram. They both share that, they both had that 6 volt delta V. And so then remember, I1, I2, This time I'm gonna have to agree with Jana. She stayed out of this. Y'all were doing this on your own.
Yeah, yeah.
No, I don't think I did. I'll tell you what, I'll rewind the recording. If there's a comment there, fine. If there's not, everyone gets a 0 for the semester. Too bad you're not under a microphone that picks up. Now you can check to see if these two are correct. How would you check that? Let's go back up to your original diagram. You can add them. Who said I don't think so? How hard is 1 + 2?
One, two, four.
2, 4.
Dude, it's kind of confusing. I just started my one follows and now. I'm just kidding.
I kind of feel like, okay, who saw the very first Dumb and Dumber with Jim Carrey? When he's trying to read the newspaper, he go to hit. It's a tough one. It's okay. Now, power and energy in circuits. Which, by the way, we finally get a warmer day in February and it's raining, but you know, at least it's not snow. Okay. Power and energy. So you see that here, the power of a circuit is either going to be I delta V or EMF times the current. Okay. So let's think about why that is. So if power is a rate of change of potential energy, what's the equation look like? Nope. Rate of change of potential energy. It's a fraction. It's a division. Rate of change of potential energy. Yeah.
Oh, why have they built these right?
But you add it in the denominator. Now, delta U can be expanded into what equation involving charge? Nope. You're thinking of gravity. You're thinking of like last semester. That's gravity stuff. So nope, it's and charge over time is what? The rate of change of charge. It's current. So there's that one. Again, your units. What's that unit? Nope. Watts. We need to get that meme back up. What? So we see that this is is amps times volts, coulombs per second times joules per coulomb, or joules per second. It's also going to have another one. Where is that? Yes. Yeah, but yeah, okay. We'll pick up here on Monday and finish the chapter, then move on.